this video, we are going to discuss how an element's properties depend on the structure of its atoms. If we recall from general chemistry, an atom is the smallest unit of ordinary matter that forms a chemical element. Before we begin, it is important to point out that we symbolize atoms with the same abbreviation used for the element that is made up of those atoms. For example, the symbol H stands for both the element hydrogen and a single hydrogen atom. Although I just mentioned that atoms are the smallest unit of ordinary matter, they are actually composed of even smaller units known as subatomic particles. Physicists have discovered that there are hundreds of types of particles within an atom, but to make things easier, we only really focus on 3 within the biological and chemical sciences. These are protons, neutrons, and electrons. Protons and electrons are electrically charged. As we can see in the table shown to the right, protons have a positive charge and electrons have a negative charge. As its name implies, neutrons have a neutral charge or a charge of 0. When observing a simplified model of an atom, we notice that protons and neutrons are packed tightly together within the center of an atom, formerly known as the atomic nucleus. The electrons, however, form what is known as an electron cloud around the atomic nucleus. Because electrons have negative charges, they are able to stay within the same vicinity as the nucleus due to their attraction to the oppositely positive charges that are present within the nucleus. This can be seen in the image to the right. It is also important to note that a proton and neutron are relatively the same size, and they are almost identical in mass. Protons and neutrons have an approximate mass of 1 Dalton or AMU. Electrons, on the other hand, have a mass of essentially 0 Daltons or 0 AMUs, since they are so much smaller than protons and neutrons. Because of this, within chemistry, we often omit electrons overall when calculating atomic mass. Now that we've established the relevant subatomic particles involved in the makeup of an atom, we can now discuss elements in more detail. Atoms that make up the various elements differ in their number of subatomic particles. All atoms of a specific element contain the same number of protons within their nuclei, and the number of protons within the nuclei is commonly referred to as the atomic number, and is written as a subscript to the left of the element's symbol. Generally, an atom is going to be neutral in electrical charge, and this basically means that there is going to be an equal number of electrons as there are protons within an atom. So, to understand this more, the atomic number of an element essentially informs us of the number of protons and electrons that are present in a neutral atom. Because we now know the number of protons and electrons within an atom through the atomic number, it's easy to determine the number of neutrons that are present through the atomic mass of an atom. The atomic mass, which is also known as the atomic number, is going to be the total number of protons and neutrons in the nucleus of an atom. The mass is denoted as a superscript to the left of an elemental symbol. It is easy to determine the number of neutrons present in any atom by subtracting the atomic number from the mass number. Let's take a look at the example involving sodium on this slide. The 23 represents the mass number or atomic mass, which, as we just established, is the number of protons and neutrons in the nucleus of an atom. So there are 23 total protons and neutrons present within the sodium shown here. The 11 represents the atomic number, which is established to be just the number of protons within the atom. So there are 11 protons present within sodium. In order to calculate the number of neutrons present, we will need to subtract the atomic number from the mass number, or in this case, the 11 from the 23. 23 minus 11 is 12, so there are 12 neutrons in this sodium. Let's go ahead and take a look at some more examples on the next slide. I have everything worked out here, so if you would like to pause the video and look over or test yourself, that is best recommended. But in the meantime, we are going to move on to the next topic, which is going to be isotopes. So now, to get a tad more advanced, we established that all atoms of a given element have the same number of protons, but there is the possibility that some atoms will have more neutrons than other atoms of the same element, which causes them to have greater overall mass. Atoms of the same element that differ masses, or atoms of the same element that have different masses, are known as isotopes. These are very common in nature, in that many elements will occur as mixes of different isotopes. Let's go ahead and take carbon for example. As we see here on the slide, carbon has 3 naturally occurring isotopes: carbon-12, carbon-13, and carbon-14. Carbon-12, or the most common isotope, has 6 neutrons and 6 protons and accounts for about 99% of the carbon regularly found in nature. Carbon-13 and carbon-14 make up the other 1%, 1% found. Carbon-13 contains 7 neutrons, and lastly, carbon-14 contains 8 neutrons and 6 protons. The 6 protons are important and must remain the same within all the different isotopes, otherwise it would not be carbon. Both carbon-12 and carbon-13 are stable isotopes because their nuclei doesn't tend to lose subatomic particles or decay. Carbon-14, on the other hand, is considered to be unstable or radioactive because it can decay. Radioactive isotopes are those in which the nucleus can decay and give off particles and energy. Radioactive isotopes are of major biological importance because they become atoms of another element during the decaying process if a proton is lost, as seen here with carbon-14 turning into nitrogen-14 through the loss of a proton. Radioactive isotopes are very useful in biological and biochemical research as well as in medicine. The next slide shows some more examples of isotopes and radioactive isotopes to kind of put into perspective that these concepts are applicable to everyday life. This concludes this video on atoms and elements. Please stay tuned and we will continue the discussion through electron orbitals and shells. Have a great day.